Now the IP addresses, because they are 32-bit addresses, they are typically written in decimal notation in 4 parts, each part representing 1 byte. A byte in decimal notation can contain a number from 0 to 255. That is all zeros and all ones. Consequently, each segment in the address is anywhere between 0 to 255. So a typical address will be 191.48.144.16 or 250 dot something something something. How will you know whether the address is class A, class B, class C or class D? Simple. No, not necessarily beginning with 1, because decimal 1 is not necessarily the first bit 1. So what you have to do is you have to translate 191 into binary and consider the first few bits to determine what address it is. There are some special addresses. For example, 0.0.0.0 means this host. That is me, myself. 255 is all hosts. 127 dot anything is a loop back. That means I am the transmitter and I am also the receiver. The host address could be divided into subnet address and a host address. So subnet is that part which describes the network address, and host address is that part which describes the host.
So why do we require those special IP addresses?
Well, for example, let me just explain this loop back thing. There are occasions when I just want to test whether my network protocol software is working all right or not. Now, rather than bothering somebody else, if I can test with myself, that will be ideal. Now, this requirement was so peculiar in the early days of networking that people decided to give that special address. So 127 is the first byte only. You determine what class address it is. You have everything else that you say is loop back. Now this was a generic provision that they made at that time. Many of these standardizations, by the way, often happen because of the whims and fancies of the early developers. There is no rational reason, just like the name COBOL came out of nowhere. Something very similar. Some standardization still makes sense, some other does not. For example, there is a multicast address, that there is a separate class for that. That makes sense when I want to multicast. But these addresses are, later on we shall see more such addresses when we come to discuss port, which is another addressing entity in the communication protocol. So there is no specific reason why these have come out like this. Now, this is the complete map of the IP datagram. By the way, a packet in the IP protocol is called a datagram, like a telegram. So telegram contains information, datagram contains information. In this you will find the most important part from our perspective is the source address, the destination address, because source address defines to whom this packet is targeted, destination, who is originator, and destination, who is the target. So these are the two full IP addresses. Clearly the width of this line is 32 bits, just 32 bit is the address. There are of course options. This is not the datagram, this is the datagram header. Along with this header will be the actual payload, which could be 1500 bytes, 2000 bytes, 5000 bytes, up to 64K. That could be the actual length of the first portion is a version. The header length, because the header length need not be fixed. Type of service that is being provided by this or is being carried out in this packet. Total length. This total length is not the length of this header, but header plus payload. So you know exactly to the last byte how many bytes are comprising this packet. There is some identification. There are a whole lot of things. Time to live is a very interesting thing. You know, when you send the packets will transfer from one place to another through routing mechanisms. Now, sometimes some jinx occurs in the routing, and the packet starts from here, goes to Delhi, goes to Calcutta, goes to Madras, and instead of landing up in Coimbatore, comes back to Bombay. And if it goes berserk, it keeps rotating like that. Now it's a drain on the resource because nothing useful is being served. Now every time a packet leaves a router, a counter is decremented. This time to live is nothing but a counter. Set at some arbitrary value, let's say 200 or 50 or 25 or something. That means I expect this packet to reach the destination in 25 hops. Every time it crosses a router, router will reduce that count by 1 while sending that packet further. So originally it had 25 units to live, then 24, then 23, etc., etc. Somewhere it will become 0. Much before that it should have reached my destination. But if it becomes 0, then that particular router where it is making it 0, it chews up that packet, saying it has lived its existence. This is to ensure that unnecessary traffic does not build up in rare cases. Okay. The exact protocol that is being used, we shall see there are two important protocols in TCP/IP. One is called the TCP protocol and the other is called the UDP. We shall see that and we shall see the implication. All other things are technical details we need not bother about. So again, in a nutshell, there is a source address, there is a destination address, there is time to live to ensure that the packets meaningfully circulate, there is a version number which is IPv4, IPv6 or whatever, and there is total length. That is, what is the packet size that is being transmitted. These are the important components here. Now we look at the transport layer. Remember, so far the discussion was about the IP layer. The IP layer is the one which takes these packets and sends them and receives them, okay? And they work with the host address, destination address, source address, etc. But something meaningful has to be done, and that happens at the transport layer. At the transport layer, there are two protocols. One is called a transmission control protocol or TCP, and the other is called user datagram protocol, which is UDP. It is this protocol which is responsible for establishing a reliable connection, transmission control protocol, and to ensure error-free delivery. So if, for example, you are logging on to a remote server, you want a connection to be established and to be retained logically as long as you are working. You don't want that connection to break. Let's say you are working on a payment gateway, or you are doing a railway reservation, or you are running an SQL query and connected to an SQL server. You would like a tight connection between you and whatever is the remote place. You are doing a file transfer. Now till the whole file is transferred, you would like to retain that connection. So consequently, the transmission control protocol or TCP is called the connection oriented protocol. It is responsible for establishing an end-to-end logical connection to retain it till your work is done, and it is supposed to ensure error-free delivery of your packets either way. Very clearly, if it has to guarantee error-free delivery, then for every packet which is delivered, it will expect some kind of an acknowledgement from the other end saying it has received this packet error-free. And that is why it's a heavy protocol. It requires more bandwidth to be utilized, but it ensures absolutely correct thing. The other protocol is called the user datagram protocol or UDP protocol. This is a connectionless protocol. There is no connection that is established. The host simply sends a packet and the packet is supposedly received by the other. It does not guarantee error-free transmission. However, it guarantees transmission to the best of its ability. You should use it only when you are not particularly keen to receive all packets necessarily, but you want quick response, quick service. Remember, I told you that transmission control protocol is a heavy protocol because it establishes a connection, so part of the protocol is vested in establishing that connection. Part of the protocol is vested in ensuring that packets reach their acknowledgement, etc., etc. But there are occasions where you simply want to send the packet as quickly as possible. Then you don't use that, you use the UDP protocol. Let me first describe where UDP protocol is used at all. After all, I do want errorless communication, right? Whichever protocol I use. So what will be the use of UDP protocol? It is heavily used for what you call one-shot request-reply queries. That is, I want to send a request and I want to get a quick reply. Or I want to keep getting replies without bothering about any request. I have made one request. Look at the transmission of speech and video. Remember, I told you that for transmission we often use IP multicast. Imagine now there are 20 centers which are receiving these video signals. These video signals at the application level are getting digitized and they are getting packetized. IP packets are flowing. But above that, what should be the control? TCP or UDP? We use UDP protocol. It's called a UDP multicast for the simple reason that when the UDP packets are going, mostly they will arrive at the same sequence in which they are being sent, because they are transmitted through a satellite channel. Secondly, in a video or audio signal, a few packets going missing actually correspond to a small glitch, but they do not affect the semantics of the entire larger information that is being broadcast. You would have heard this, when you use a speech, that is, if somebody is talking to you from across the continent, sometimes you listen to a small glitch. That glitch is happening because maybe a couple of packets have just gone away. The packets are very small. Many packets together make even a sensible 0.5 second audio or video. So consequently, a few packets getting lost really does not matter in some situations. But even for voice and video, when you want an absolute guarantee, you will use TCP/IP. On the other hand, using UDP ensures very quick transmission because there is no overhead. You just take the packet, throw it. Typically for multicast, you will always use that. And there is one more usage that we will see later during this talk itself. So this is error prone, but less deal. Connection oriented and connectionless in our normal life, we should compare with connection oriented to a telephone call, as I mentioned. A connection is established, logical connection. Connectionless to a postal service. I send a lifafa to my friend. I drop it in the post office box. This is a datagram which has left me. It will travel through various post offices till it reaches him. I am not waiting for acknowledgement. And I generally assume that the letter will reach my destination. Once in a while I read in the newspaper that somebody received a letter after 15 years. But these are rarity. And I have to live with that. If I want an acknowledgement, and if I want to create an effective connection-oriented thing, even though spanned over many days or months, I will use in my postal services a facility which is called acknowledgement or registered AD, acknowledgement due. That means whenever you reach this packet to the destination, please send me a small piece of paper with his signature. That may happen over multiple days. But if I want that connection-oriented protocol, it must happen in milliseconds. And there is an overhead. The postal department has to work extra hard to take that signature, send it back all the way to me, ensure that I receive it. And any time I can go with the original receipt to the post office saying, what happened to this? I had sent acknowledgement. So that is connection-oriented, and connectionless is simply dropping an envelope. So TCP and UDP are exactly like that. At the transport layer, let us look at TCP. This is called the Transmission Control Protocol. This is a reliable end-to-end byte stream. It takes data stream, that is a file to be transferred. Consider a file is, let's say 28 megabyte file, large file. Now you want to transfer it. 28 megabyte cannot fit into a single packet. So that you will actually, when you do an FTP, at the application layer, the FTP will connect the byte stream. It will open that file and connect that byte stream to the TCP protocol. The TCP protocol will keep connecting bytes and keep building IP packets, which are all smaller than 64K. And then will send these IP packets through the IP part of the net. But because the transmission control protocol is in command, it will expect an acknowledgement for every packet and it will ensure error-free transmission. To establish a connection, a logical connection, TCP protocol uses an additional mechanism of addressing. Remember, IP address is there for the host, IP address is there for source, IP address is there for destination. But to establish a connection, there has to be something more than just the IP addresses. And that something more is in the form of sockets. So the sockets are created at the two endpoints, and there is a virtual or logical connection between the sockets. Each socket has an IP address, as is well understood. Additionally, it has a port number, which is a 16-bit port number. Port, you will recall, is like a seaport. You know, ships come and dock there at the port. So a ship coming from England could dock into Mumbai, could dock into Kandla, could dock into Visakhapatnam, could dock into any one of the ports. So this country, which considers a single IP address, has multiple ports. And maybe US ships will dock here, UK ships will dock there, Malaysian ships will dock in Visakhapatnam, whatever. I might have my own arrangement. Exactly similar to that, in programming, I can make arrangements such that I can have multiple sockets. Each socket is one host address and a port number. It is possible to open multiple sockets on the same computer. I just have to have a different port number for the same IP address. So this is the connection oriented mechanism that TCP provides, and socket programming is a well understood, well analyzed and well required programming paradigm for the software professionals who do programming at the communication protocol level. So if, for example, you have a Java application which has to communicate with a database server at the back end, the way this Java application will communicate with the database server will be using the TCP protocol. And internally it will open port here, open port there, connect the port and send queries, collect results, whatever. So that is the importance of this. Remember, IP address is 32-bit and port address is 16-bit. The connection is always identified by pair of sockets. So at one end socket 1, at another end socket 2. Now somebody was asking about standardization. Here is some more standardization. Ports which are less than 256 in value are used for special services. They are called special. There is nothing special if you see the plethora of applications that you have. It is only commonly used applications which have been termed as special and port numbers have been assigned. So if at all you are doing FTP, file transfer, the FTP or file transfer protocol will always use port 21. Telnet or making your machine as a terminal to another machine will always use port 23. The connections are called full duplex. That means information can flow both ways, from here to there, from there to there. So socket to socket is as if connection, and IP packets can flow across, acknowledgements can flow across, and you have a true error-free connection-oriented protocol. Of course, connection can break at any one point. But if the connection breaks, it is guaranteed that you know what is the last packet transmitted which has been received correctly by the other. The data is exchanged in segments. There is a header, TCP header, which is a 20-byte header plus options, and then it has data. So here is the TCP header. So TCP header has a source port, destination port. It has a sequence number. It has a TCP header length, flags, window size, acknowledgement number, checksum. Remember, no bit has to be lost. This is the job of this layer to ensure. Although at every layer the protocol tries to ensure correct transmission and reception, but this is the ultimate responsibility. So checksum is nothing but some kind of a numerical value coming out of the entire packet. So if this is the packet or the header or the whole datagram plus TCP packet, then there will be checksum for that. There are then options and there is data. So this is what the TCP header is. Please note that we have a source port and destination port number. Take UDP. So UDP has a source port and a destination port. It has UDP length and UDP checksum. You see how simple the UDP packet is. You do a datagram protocol because it has to define where the source is, where the destination is, and this is the UDP header format. It sends and receives capsules of raw IP datagrams. So it will capsule the raw IP datagrams and send them. The individual datagrams will move an IP thing. Okay. Now comes the thing which is important from our perspective. We as human beings are not good in remembering numerical identities. I don't know, some of you remember phone numbers very well, but I find even that difficult. In general, to remember that his IP address is 191.16.144.73 is not going to be easy. Somebody wants to address my machine, he would much more prefer it to be saying something like dbp at it.iitb.ac.in. We recognize those addresses. Consequently, a simplification of address occurred. Very early in life, in ARPANET itself, there used to be a file called hosts.txt. So this was a text file. And this file actually contained the name of the host and the IP address. So it could be used as a translation table. Even today, /etc/host, for example, would be able to give you exactly the same kind of thing. A domain name system was soon evolved, and this domain name system defined a hierarchical addressing scheme. For example, the last component of that address is a generic address such as .in, .jp, .uk. You can see it stands for India, Japan, UK. There have been .us, but US did the dadagiri because they originated the network. So they said that whenever there is no nation, then it is me. So those addresses now are called generic addresses. These are .com, .org, .edu. They don't, if I have .edu, .jp, then it's an educational institute in Japan. But .edu invariably means an educational institute in US. Of course, to be fair, they became very, generous about it, and they said, let us call these as generic names. That means even you and I in India, Japan, Czechoslovakia can have a .com address. Invariably all .com and .org addresses are still served from servers within United States, but that is incidental. But these are called generic address. The next level could be, say, CO for company, AC for academic, ERNet for educational research network. A level below that could be IIT Bombay, TIFR, persistent systems. Below IIT Bombay could be IT, CSE, mechanical, AE, etc. etc. So quark.it.iitb.ac.in is the name of a server. It's a host machine which is located in IT, which is located in IITB, which is located in the academic subnetwork of Indian Net. This is a unique address universal. Of course, the machines at the level of protocol don't understand a damn thing about such address. They understand IP address. Consequently, the domain name system must provide for some kind of a simple and automatic translation between the addresses which are given like this and an IP address. Well, IP address is what will be used by people. This translation or address location is done through machines which are called DNS servers. So they just handle domain name system and domain name servers translation. The domain names are case insensitive. They are either absolute or relative. Each domain controls allocation of names under it. Oh, NCST in India is wrong. The National Center for Software Technology used to control the domain names. Now, no single organization controls the domain name allocation. There are commercial people who allocate domain names to you. There is a registry maintained by the Government of India. NCST itself does not exist anymore. It is now part of CDAC. Okay. They still have a role, but that is how it is. The length of the name can be 63, any individual name between dots, and the total must be 255 characters. That's the restriction that was imposed earlier. How do you resolve a domain name? Because networks understand IP address. To resolve the domain name, you have a name. You give that name to a server which does this resolution. That server does some jing bang and finds out the IP address and sends it back to you. So, the purpose of a DNS server is to take a name address that is given, as in quark.it.iitb or whatever, and send back resource records. One of the resource records contain the IP address. The DNS server is, by the way, very well organized. It just does not do only this. It can do many more things. So all the records in DNS server are called resource records. These are resources about the domain names. And one of the resource record, in fact the first one, usually will have an IP address. Now please note that if you want to communicate with the rest of the world using the named address scheme, the first thing that you have to do is to get an IP address. If you can't get an IP address, you can't communicate. Unless you are communicating using exact IP address yourself. Now this task will be required how frequently? Very frequently really. Everybody, in order to initiate any communication, will require to resolve this. Once you resolve this, maybe you will bury that IP address in your application somewhere and keep using it. But every now and then, you go to any website, for example. How do you go to website? You give a web address which is like this address, DNS address. It has to be resolved. It has to be resolved rather quickly. To resolve this, you don't want to do socket programming and open a socket. That is where you use the UDP protocol. Remember what I said when we discussed the UDP protocol? Single request response kind of thing. This is exactly the case. I send a request. I have this name, give me IP address. And that sends the IP address. I don't want any overhead, so I send it. Consequently, I send it where? To a DNS server. the first thing that every machine must know which is on the network is the DNS server which will be utilized by that machine to resolve these addresses. So in your network parameterization, for example, you will find the name of the DNS server to be specified. Of course, there is always a default for a local area network. There is a default DNS server, default DNS gateways. The point I am making is, you use UDP because you send this packet very quickly, saying give me the IP address. And usually the DNS server quickly searches and sends you the IP address. Now, this is not an error-free protocol. Suppose you don't get back anything. You don't lose anything, you send the request again. After all, if you send the same request 10 times and you got the response 9 times out of 10, it doesn't matter, you're not harming anybody. You can afford to keep sending the request till you get the DNS response. And since you don't want to waste overheads of connection-oriented protocol, you use UDP for that. This is, by the way, a standard question which many networking experts have failed to answer. Give the most simple UDP utilization in real life. That utilization is DNS resolution, because you don't want to waste time in overheads. So it would be cool for any one of you to ask any friend from computer science, saying, do you know where UDP is used? They will typically say voice, video, etc., but they will often fail to recognize this.